Horrible packing job, ahoy! Oh yeah, that's padded by one layer of cardboard. Oh, that's gonna help. Oh yeah. Well, it was a battery door. So, eBay special. This is a patient monitor. This is, you know, basically a hospital surplus. I should probably actually wash my hands after touching it. So this is basically one of those things they put on like the IV cart in hospitals, and it does all the fun patient monitoring stuff. If you look over here, there's actually SpO2, which is blood oxygen concentration, a 1/4-inch phono plug for a temperature sensor, something for a blood pressure cuff, EKG, ECG, that's going to be electrocardiogram, and then there's IPB1 and 2, and I'm not too sure what those actually are. So what this is basically, you know, a full-blown, you know, it's got all the fancy pants stuff that people use, you know, in hospitals to determine whether somebody's, you know, still alive or not. So I got this for 20 bucks, plus $20 shipping. I think this stuff gets old and then they can't use it anymore. I think they have to have it recertified or something like that. And recertifying it is so expensive that they tend to instead just buy new ones. So the funny stuff on the display is actually the LCD monitor I use for viewing my, basically for seeing what the camera's seeing because I'm in front of it, not behind it. So this is kind of disgusting. But you've got, you know, ECG, electrocardiogram, IBP, I'm not sure what they are, NIBP, which is non-invasive blood pressure, start interval. So this basically, it'll take the blood pressure measurements periodically, record, DC input, trending, alarms, you know, when the EKG stops, the alarm goes off because, you know, hey, his heart stopped. Kind of important. And it's got a big display, and this looks like a plasma display, I think. You know, basically one of those orange displays. You can see over here it's got a printer. Hey, it's even got paper in it. And then it's got 2 batteries. So these are going to be for, so the thing can basically be self-sustaining, and it's going to have 2 batteries so that 12 volts, 2.3 amp hours. These are going to be, these are, feel like lead acid. So, you know, 2 batteries so they can swap them when it's on, and power outages, and the person can be mobile and carry it around. I wonder how long it runs on this. You know, so it has 2.3, so it's got 4.6 amp hours total. Ugh, it's all kind of disgusting. Looks like the... I know, that's just foam from the splendidly not effective packing job. Then you can see back here, it's just serial numbers, part number, and then there's this interesting thing which probably hooks onto some sort of cart mechanism. Some sort of sticker. So, it has a very strange power connector. All of this stuff is going to be completely custom because, you know, you can't have people like plugging their cell phone into, you know, something that's possibly responsible for keeping somebody alive. So here's the DC input, and it's got these 4 little tab jacks and then a screw in the middle. And then this is probably for pulling data out of it. On the other side you can see SpO2, cuff, EKG, blah, blah, blah. And the interesting thing is all patient connections are electrically isolated. So there's going to be a lot of really high quality electrical isolation in here, which is one of the reasons I wanted to buy one of these, to take a look at the internals. Standards for getting stuff certified for patient connection, you know, especially with like EKG leads, which use conductive gel electrodes. So they basically, they punch through the skin barrier. So if you're getting shocked, actually one of the biggest barriers to getting like a really severe shock with low voltages is the fact that your skin is a surprisingly good insulator. That degrades heavily if your skin is wet, especially with salt water. So, you know, and actually what they typically use is they use these little self-adhesive gel electrodes that have basically like it's a disc of adhesive, like a sticker. And in the middle there's like a little, one of those buttons, those snap-on buttons. And then, you know, it's metal. And then on the underside there's a little sponge filled with conductive gel. So you kind of stick it onto the skin, and the sticker around it keeps the conductive gel in there, and the conductive gel makes the connection to the snap. And then the leads just come on and they kind of clip onto the snaps. I worked for a company that makes, biological measurement. I worked for a company that actually makes stuff like this for a while at one point. So, yeah, interesting. Like, I wonder what the hell this is. Looks like there's some sort of sticker cover. And then this, obviously, goes over here like that. So, you know, and then it just got fucked up in shipping because the guy grossly underpacked it. You can see it just uses, it's a little thermal printer. So I'm really tempted to kind of try and power this up because I'd like to see what the display looks like. The issue is I don't have any way to... Where's my slotted screwdriver? That's a stupid idea using that. So this is marked Datasette, which makes me think it's probably got some sort of obnoxiously proprietary memory card in there. I think it just came a little loose, or it could not be installed on this particular unit. A lot of these have lots of options. Oh, guess not. So, Datasette, caution, turn power off before removing, in 3 languages: English, French, German, and Spanish, I think. Yeah, so I bet we've just got 2 little EEPROMs in here. Probably high write endurance EEPROM. You know, and they're just 2 little... That's very adorable, isn't it? I might see if I can figure out how to get data off of those. Probably a HIPAA violation in there somewhere. The fact that some people are selling this shit on eBay. So, let me just... Why don't I just pull off the back? So the first thing I'm going to do is take off this big metal bracket, because I don't know if these screws are involved. Nope. So I expect this to be really beautifully made internally, because so much of the cost in making medical equipment is in the certification, that overbuilding it is, you know, it's like sending food to astronauts. You know, it costs so much money per pound that making the food high quality is, you know, not really even a relevant cost. There's nothing under that. So I see 3 screws up here. Like this handle, that's die cast from the feel of it. Actually, that's interesting. What is this? There's a little metal danger, possible explosion hazard if user in the presence of flammable. Oh, I think they're, oh yeah, they're possible explosion hazard if used in the presence of flammable anesthetics. So basically they're saying that this isn't explosion safe. And there are some anesthetics that are actually flammable. I don't know what they are. Basically some of the gaseous anesthetics they use can catch on fire. So, you know, they have to have special explosion safe equipment for that sort of thing, and this is apparently not one of those models. Apparently I can't read anesthetics upside down. That's interesting. It seems like the screws are captive, because this is a magnetic screwdriver. Oh, I guess this one isn't magnetized. Isn't one of these? What's my magnetic screwdriver? Alright, I'm just derping. Oh, yeah, they're not captive. One thing you might notice is that all of these screws have little spots of thread locker on them. See that red and goop? You know, again, other stuff to try and maintain. And they're basically just really high construction standards. And I am going to scrub the crap out of my hands after handling this. It looks like it's got all sorts of interesting biological fun on it. Probably also hit my workbench with a disinfectant. Alright, those three are loose. Sounding promising. How many came out? Just one. Actually, now that I think about it, I should probably eject the batteries. Oh, yeah. These have been in and out a fair number of times. Nice scuff marks on the top. Another thing you might notice is that all of the screws I've taken out so far have gone into metal inserts. Okay, the front panel is kind of loose. Okay. Yep, see, there goes the front panel. Alright. So, interesting. So all we have is one very large ribbon cable. So, looking in here, here's this edge connector for the memory, and this is an EDAC edge connector. These are very expensive connectors. The size of that capacitor. Big ass axial cap. Motorola micros. And then in here we just have various buttons. This is it looks like an off-the-shelf LCD module. And then it looks like there's some sort of switching DC to DC down here. So if we look down in here, you can see there's some sort of switching supply here. And I bet that's generating the high voltage because I think this is one of those old orange plasma discharge LCDs. Or, well, it's not an LCD, it's a plasma display. Which is quite cool. The other thing is if you look over here on the power connection, you can see that it's connected straight into the side of it. Oops. It has 4 leads. I was kind of hoping I could figure out what was what and then just apply power that way. There's our power switch. And then you can see that it looks like this connection here is indeed for data of some sort. Oh yeah. Let's see if I can't kind of walk this ribbon cable free. So we're seeing a number of things of interest already. Here's the front panel. So you can see that we have a very heavy metallic spray-on EMI shielding. Actually, that's an interesting idea. Use my new fluke. Get some more light on the subject. So, yeah, look at that, 1.9 ohms, 3 ohms, and these test leads are, they're pretty low resistance. So, you know, this is an extremely heavy shielding coating on this stuff, you know. And it wouldn't surprise me if the front panel of this is like a lead glass of some sort as well. They're going all out for this sort of stuff. So, we'll put this aside. So we can start to kind of see the system architecture. It looks like this is the front end for all of the connectors. Got a microprocessor board here. And then you can see that this is just a little cable going into there. And then I think the power supply is kind of on the back. The power supply is back in here. So it kind of looks like the internals come out as a unit. Oops, there go the rest of the screws. Let me see if that's true. Let's see. One screw here. And one screw here. There's your other snug. So I think, yep. So this board this whole thing is very nicely engineered. So it looks like this is held in by several cables. Got a ribbon cable there. Ooh, fancy, this is a latching connector. It's like an edge connector. And then there's whatever this is down here. It's probably power, considering it's got lots of disparate cables. Oh, yeah. that is mostly it, except for what appears to be, oh, the pump for the NIBP blood pressure cuff is back in there somewhere. So, let's see if I can't kind of just yoink the power supply module out. Oh, there's all the connections to the batteries. So here is the power supply. So, I'm going to set this back down. Okay. So here is the power supply module of whatever. So we have, yeah. So power comes in here. There's probably communication through some of these connections, though I'm not sure. It has 3 fuses, probably 1 per battery. Yeah, I think so. Four amps low blow, 4 amps low blow, 2.5 amps low blow. So the real question is, why are there 4 leads on here? Because I'd like to just tack power on here. Here's the other power supply board. You can see there's some interesting stuff here. We've got a little switcher. And then there's actually a current transformer on the PC board, which is kind of interesting. This is a FET. And then down here we have... oh, these are all diodes. Okay, so it looks like this is all diodored together, and then over here there's a big power DC to DC switching brick. And you can see the ground is brought over here too. Oh, I think I know what's going on. I think some of these are safety ground. Wonder what this connector is, because it didn't seem to be used. So let's see, there's the output, and here's the input. Fortunately, I can't follow the traces under the module very easily. So that's 1, so that's plus. Can't tell where that's going. Alright, let's get the ohmmeter. Because I'd like to power this up before I take it all apart completely, because I probably won't get it back together after I've fully disassembled it. Put it in ohm mode. So let's see. Okay, so that goes to the fuse, and then that goes into the diode. So it looks like this, I would bet, is the positive rail. No, it's not. So this is V in plus right here. Okay, so that's brought over to that connector, I see. There's some switching FETs on here. So that's that connection. So those are all fairly heavy. So this appears to be going there. Oops, no, I should just switch. So that's got a VF of. I don't know if you can make that out. So anyways, I'm measuring the VF of these diodes, and they're about 0.175 volts, which means that these are Schottkys. these are all Schottky diodes. So oh. I think I see what's going on. So it looks like there's a ground. Yep. And then there's a VCC. And then I think, so the way this works, it looks like the battery charging electronics are separate, I think. So that should be VCC. Oh, I think I know what's going on. I think it's switched off. You plug this in, turn the power on. So this was the VCC. So, yeah. Okay, I think I see how this works now. So, volts. So red and then yellow, I think. Well, it'll either blow up or work. Or both. I'd be okay with both. I'm assuming the hot is fused because the ground being fused wouldn't make any sense. Yeah, drawing 700 milliamps. So. Ah, fuck, that scared the crap out of me. Yeah, so we have 12 volts here. Okay, so. When I turn it off and it draws nothing. Alright, so now I know, whoops, shorting shit out. That yellow is ground. And orange is hot. So, pull back the heat shrink. Alright. Tenacious stuff. At least it's not the kind with hot glue on the interior. That is ground. This meter is kind of cool. Basically, one mode does everything. I can get behind that. So the nice thing is it looks like the inputs are all totally diode protected. So I think it would be somewhat involved to actually damage this from the misapplication of the power supplies. Anyways, so he's off, drawing no current. Fuck, it keeps startling me. That is going to go on. Oh, hey, look, it's keyed. That's it then. Put a little more bend in that. Where was this ground going anyways? I can relocate that. Yeah. wow, that was tight. Was that appropriate considering it's a safety ground? So, I think these ribbon cables, I think this one is probably for the, it might be for the printer, I'm not sure. It could be for the NIBP. And then this one is for the other one. This whole module is kind of bent a little bit. Everything's keyed. It's quite nice of them. So, I don't know what just happened. I gotta give it more current, I think. Something's happening. Hey, look, we've got shit on the display. DC input is high, and it's drawing 1.25 amps. Hey! It's alive, and I think I know why they threw it out. Hey! No, really? But if you look, there's a couple lines on the display that are missing. You know, which is typical of these plasma things. It's also bitching that the battery isn't there. Oh wow, that shit's loud. We're ordering ECG, alarms, SpO2 85%. This is the IBP. I don't know what IBP stands for off the top of my head. NIBP, non-invasive blood pressure. IBP, could that be invasive blood pressure? So we've got RESP. So it looks like they have like a chest transponder that measures chest. HR, I'm not sure. SpO2 is specific oxygen. That's going to be the basically the blood oxygen content monitoring. This thing makes a lot of noise. Is that the NIBP doing something, or is it just like a DC to DC in there squealing? Obviously everything, SpO2 new sensor, NIBP, idle. Let's see. Holy boy, I think I made it sick. So that was me attempting to fire up the blood pressure. I think it just was convinced that I had like a 197 millimeters. I think it's convinced I have a heart issue. Because there's no reservoir on there, so it's just pumping up the tube and then going, oh fuck. Deflate, unable to measure. Let's see, interval 1 minute, 2.5 minute, 5 minute, 10 minute. Yeah, so you can set up the intervals at which it does an automatic NIBP measurement. And then it looks like you can set up the speed, the rest speed. So it's got a cascade EKG, it's got a PLEF, which is a plethysmogram, which is an optical blood pressure measurement mechanism. Rest source. Oh, that's it. So considering they're saying ref source is ECG, I wonder if they're doing like they're using the EKG leads or the ECG leads. EKG and ECG are the same thing. They're just, you know, I think EKG is German originally because electrocardio. I think what they're doing is they're using the ECG leads as an EMG to measure respiration rate. I'm not sure. That's interesting. It's got a whole bunch of lead options, size. Well, that's interesting. I just heard a relay. freeze. Oh, I think, you know, most of these have multiple leads, so I think this lets you look at multiple leads. Man, that sounds a little ill, doesn't it? I'll turn that off. So that's the alarms. Oh, hey, look, it's trying to print something. I don't know what it just printed. The printer looks like it's not working either. Because I would think it would put some text on it at least. Oh wait, no, it just did something. Oh, cool. So here's what it printed. You can see it's it's a little EKG plot. It's pretty nice. It looks like it does like this nice like grayscale chart. It's very cool. Patient name blank. Shows you the leads. Oh, that's cool. 25 centimeters per millivolt. Oh, that's the Y scaling. Speed, source, frozen key. I'm not sure what that means. There, it's printing another one. You can see the print speed changes as it's doing different things. Whoa, it's printing a long one now. Oh, it's because it's been recording for longer. What the fuck? Did I make it sick? Yeah. So I guess that's all the memory it's got. Lots of it. Yeah, look, hey, I hit the freeze key and it stopped. Apparently the freeze indicator is now off. Yeah. So, cool beans. Seems to work. It's complaining a little bit about the battery, which isn't surprising. But yeah, it seems like the way this works is the reason this has 4 leads is that 2 of these are dioded into the battery. So I think the battery can, you know, basically the battery charge is probably part of the external DC input. This goes down hard. Takes quite a while to start up. So you can see here with the, you see the little triangle on the corner, you can see how there's a stripe in it, and that's because the way these work is they're, if you look in there carefully, and see if the camera will focus that close, you can see those little lines along the edge, and so there's horizontal electrodes the whole width of the display. There's basically, these are offset from those, so they only have to have every other line on each edge. So that's the EKG starting up. So what I think happens is one of these lines, the driver for the line will go bad, because this is actually a plasma discharge. I think they've got an associated vertical line assembly and they have a plasma discharge between the two, and it takes like 50 or 80 volts or something in that range. Actually, I wonder if... What is so noisy in this thing? Does it have a fan in it? I wonder if I can find the voltage, the high voltage on here. I'll look into it later. Anyways, power off. It also draws about 12 watts. So you probably get about 5 hours on these batteries. You know, because it draws an amp at 12 volts, and each battery is 12 volts at 2.3 amp hours, so that would be, well, it'd be 4.5 hours. Doesn't feel warm at all, which is good. Oh yeah. This is an interesting little power supply module. So it was just kind of sitting in there. You can see it's got leads linking the two together, just a really tall connector. There doesn't seem to be any mechanical support, which was very strange. So, let me take these 2 cables off. This one has latching. Oh yeah, and then I have to do something about the frickin'... fortunately, it's got a connector here. So you can see in here, this is probably the NIBP. You've got the battery caddies down here. Oh, look, it has little edge slots. So this is where the two power supply boards sit. Battery carrier, and this is the printer. And it looks like this cable is going to the printer, and this cable is going to the NIBP. Wow, this thing's actually quite busy. It's got two big circuit boards on it. So that's interesting. This is all going right out the... Oh, of course. So one thing you might notice is that basically this board is unisolated because there's no isolation gap on it. You can see that this connector here is just going straight into this board, which is connected straight to the power. So this is all unisolated, or it's as isolated as whatever the power supply they use to run these can be. But because this connector here is the SpO2 sensor, and SpO2 sensors are not they don't have an electrical connection to the body because it's generally done optically. So that means that this board is, first I'd guess that this board is the SpO2 transducer board. Considering how old this thing is, it seems like it's all dip. It takes about that much, or one really big DSP these days, to do an SpO2 system. So I bet this is like an SpO2 system they bought off the shelf or something along those lines. Actually, let me move the camera and then we'll continue. Yeah, this is just the same board. You can see revision status all the way up to revision 21, and they circled 1. So we can see here that this is an HD63C09, so that's probably a microprocessor. Sony CXK58257AP. EPROM and another EPROM. These are probably flash of some sort. I don't have an EPROM reader, unfortunately, so I can't pull the contents. This is interesting. Look at all of these. These look like silver mica dipped caps. So they've got some really fancy analog stuff going on up here, which makes sense. It wouldn't surprise me if they're using like a lock-in amp or something to pull the to try and recover the signal. I'm not too sure how SpO2 sensors work. They look at, basically what they do is, as I understand it, the color of your blood vessels, the red blood cells in your vessels change as the oxygen content varies. So they're going to be monitoring that in some manner. It's complicated and I don't really understand it. I haven't really done much with it. And we can see down here, one of the few socketed dip 8 part, or narrow 300 mil width dip parts is an 87541AJN. This is all 7400 series logic. 74's C374, yeah, chip treasures and shit like that. This is all 7400. It looks like, it looks like this thing probably has a parallel interface, considering how freaking many wires. And kind of the ridiculous, that's like what, a 50-pin connector? Yeah. So I bet this is a parallel interface, and this is probably interface, buffering and shit like that. It's possible that that's how they get from like a 6 or an 8-bit microprocessor bus to a 32-bit or something like that. All this stuff up here, DG201, that's an analog switch, analog switch, OP07, OP07, that's an OP27. Yeah, this is an OP27. That's a fairly expensive op amp. We use some of those where I work for high performance data acquisition stuff. A lot of that stuff, it's a TLO82, I think. No. So that's a TLO82, and this is a TLO32. TLO32, OPO7, OPO7, TLO32, TLO32. LM311, I think that's a comparator. LF398 from Philips. And then there's some, here's a canned IC, and then here's probably a Q4. So this is probably like the high performance analog stuff over here. Q5. Some discretes. Here's something with a rev number on it. 0155-90. I bet this was made in 1990. I don't see any. Well, 9629. Could that be week 29 of 1996? That's the only date code I see here. See if I can't get this sticker off and see what this is. I bet it's just a PAL or something along those lines. Oh, yeah. Yeah, 16V8. PAL C516V8, I think. Oh no, CE16V8Q. Yeah, that's just a PAL. That's just a programmable logic array. I wonder what this is. This CXK58257. Anyways, interesting stuff. Just look over here. Here's the microprocessor section. Get some more light. You can see, look at this heavy ribbon cable. You can see that they've got like a manually inserted key. Yamaha V6366. That's probably one of those sound generators, I'd guess. Some interesting chips on here. This is, you can see here, this is an MC68302 FC16C. This is a 6800 series microprocessor from Motorola. This Yamaha chip interests me. First of all, the date code on this is 1986. It's got, actually, it has some Japanese lettering on it. You know, Yamaha, as far as I know, mostly made sound chips at that point. I don't know what this is doing. Here's another PAL. This one's Rev B. DG201, TLC54, no, 541. Other interesting stuff. Here's a comparator. This connector interests me a lot. So this is like, you know, you have like an 8P8C connector for, you know, phone, for Ethernet. This looks to be like a, it looks a hell of a lot like a 20P20C connector. But it looks like the phone plug kind of style with the pins in there and everything. That's quite unique. It's got a lot of pins too. We can see here we have more Sony chips, CXK58100AP. I bet these two are probably SRAM or something for this microprocessor because I don't see any other RAM. Got a couple clocks here. This is a 14.318 megahertz clock. That's an interesting frequency. This slightly bent over crystal is 16588.8. Could that be in kilohertz? Could that be 16.588.8 kilohertz? Because I really have, I doubt it's 16 gigahertz. That's weird. Here's this little card slot. You can see these two things, little bypass caps. You can see there's lots of bypassing on here, particularly down in this corner. Look at all of the bypassing, and there's these great big epoxy blob tants. 74HCT 244, 74HCT 244, 245, 244. This could also be SRAM, I don't know. And then you can see here's a little lead going into the analog casing. It looks like this is the cable for all of the analog stuff because I don't see any other interconnects going into there. You know, fortunately most of the, you know, human, you know, meat puppets are kind of low bandwidth, if nothing else. You know, we're not very high bandwidth. Computers run really fast. Here's a little time watch crystal. It's probably for the internal RTC, and this is probably the RTC backclock. This is actually a DS1236, so this is going to be the RTC IC. Here's a Max 232, so that's going to, so there's some sort of serial transceiver on here. This is kind of interesting. It looks like there was some additional stuff here that's now jumpered out with just this little wire. And then there's this great big 10,000 mic at 16 volt axial capacitor. I wonder if this is like some sort of RAM battery backing or something like that. Or, you know, maybe there's huge pulse draws from the printer, which wouldn't surprise me, because it's got thermal print heads. So, let me just, carrying on. Where is my big, there it is. This should be the really interesting stuff, and then I'll just diverge into the blood pressure sensor. Oh, yeah. Very nice folded metal shielding. You can everywhere you can see it. Now we get to the fun parts. So here we have the front end for the analog section. So you can see that right in this corner, if you look right in here, you can see we have some optos, and then we have this. This is very interesting. This is actually two transformers in series. And what they're doing here is using two transformers in series gets you a higher isolation rating. Actually, one of the places I worked used this exact technique with off-the-shelf transformers to get an isolation rating that was basically something they could then use for medical equipment. So this is apparently a fairly common technique. So it actually, how is this wound? It looks like there's center tapped on each end. Yeah. So it looks like it's halfway center tapped on each end. This is interesting. We have two pot core transformers over here. No, that's not. These aren't pot core. So it appears what's going on is, oh wow, this is a choke output power supply. So transformer comes out here, it's full wave rectified, and then it goes through a choke, and that'll really kick down your high frequency crap. That's a choke output filter. It's it reduces your total overall voltage, but it also really seriously, reduces your noise level. That's pretty cool. So this whole section here is the output chain, and then it looks like the power supply chain. And I bet, so the isolation barrier is right along here and then down here. So this is the non-isolated section, and the rest of this is completely floating. But you can see that the power kind of comes in here. It actually, these two devices here are the switching devices. And I bet this here, this is an SG3525. I would put money on it. That's probably the switch mode power supply controller. Another thing of interest is it looks like, I'm not too sure, but they very well might be running this open loop and then just post-regulating. So in that situation, what they basically do is they just drive these with a fixed duty cycle. Probably I'm not sure if it's a sine wave or a slope limited square wave or something along those lines. But they drive it with a fixed duty cycle, and then they just have post-regulators on the other side. Let's actually see. These are MC78L05. Yep. There's two 78L05s. I don't know exactly what they're doing, but that's intriguing. And you can see here we've got some additional... oh, hey, look, there's a whole other board under there. Little micro, I would bet. This could also be SRAM, but I bet it's a micro. See if I can't get this sticker up non-destructible. So they probably just have, considering there's two optos, this is probably just serial communication along here. MC68HC705C. It's another 6800 series microprocessor. They sure like those things. Then we have just, this looks like it's almost entirely analog. So we've got your power supply here. Here's an oscillator crystal for all of this, I would imagine, which is, what is that? It's 3.6864 megahertz. And then we've got, and this is an LT1013 TL1232. Unscrew these nylock nuts that hold this extra board on. So this is quite interesting. So you can see here we have another little board, and that's interesting. This whole thing just kind of, oh hey, I didn't need to unscrew those. So it looks like this is just held on by being squished against the interior of the case. That's amusing. So some of this is probably modular. They probably offer different options on this, which maybe, there's like a baseline, and then you can, say, oh, I want SPO2, or oh, I want NIBP, and then they can, stuff the module and, probably change some config bits in the firmware or something. So one of the things you can see down here, oh, hey, this is all the interface. This is everything. So that's interesting. Let me disconnect this, pull the SPO2 connector. And the other thing you might notice in here is the recalculous ground strapping. Look at that. There's the ground strapping. There's a strap to this there's this huge like 12 gauge or 14 gauge ground strap running into the SPO2 interface, And there's this other huge ground strap running into the, so everything is like grounded out the orifice of choice. So we can see here that we have, look at that. Is this like a mux board or something? This also looks a lot more recent. Look, it's got surface mount parts all over it. Whoa! Spark gap. Are those neons? Wow, trippy. So, let's see. I have to pinch these two little inserts to pop it through. There's one, and there's the other. All right. So man, look at this. This is really kind of weird. So first of all, you can see that here's the temperature sensor input, and it's going. All three of them are going through a little ferrite. It's marked L1, and then the traces run over here and then down into this board. You can see there's actually a so this is just a little ribbon cable. It's a weird little module. You can see this is all flex PCB. This is 2-layer flex PCB too. That's expensive stuff. You can see there's a copper layer down there. You can see these run up here and then down there and then through there. And I don't know what all of this stuff is for. These are all marked CR. These might be Zener diodes or something like that. They're sure chunky. These are all 1N6275A. You can see here's a whole pile of silver mica caps, fancy pants film caps. Wow, these are 3 kilovolt film caps. And then look at that. There's resistors and heat sink tubing, I think. Or is that? That's weird. More R5, R7, CR3. There's a spark gap. Oh, that's interesting. Look at that. The spark gap is between the ground and the rest of it. So this is probably, you know, basically to discharge the patient. You know, if that's to, you have a spark gap and then you have probably a really high, that's a carbon comp resistor. And that's, let's see, it's brown, black. So that's 1O purple. My sheet doesn't even have purple. Though what I can do is, where is my fluke that does measure high impedances? I'm dropping shit! Bug. I need to clean off my workbench. So. Either that resistor is bad or so enormous nothing I own can measure it. Let's see, auto, and I want to be on kilo ohms. See, am I getting a good connection? Yeah, I'm getting a good connection on that end. Weirdness. So, it's the over resistor. But you can see, let's see, EKG leads come in, they go through whatever the hell this is. These weird shielded resistors. What is the neon across? I think the neon is to ground. But anyways, this is a very interesting little board assembly. Looks like there's all sorts of fairly involved diode, resistor and diode clamping and other shizzle like that. It actually looks like the signals are going... Okay, so the signals go through resistors and then the diodes clamp it. These might be like transorbs or something along those lines, I'm not sure. Oh, that's interesting. Look at this cable going to the NIVP. Every other lead is cut. So they're probably using that to give themselves a lot better, isolation between the wires. That's kind of interesting. And then it looks like there's a whole bunch of stuff in here. Oh yeah, look at that. I bet there's ferrites and diode clamps in here as well. Yep. There's also, look at that, there's a whole suite of diode clamping in here too. That's kind of hackerific. It's all zip tied together and... is this glued on somehow? No, it's just really stuck. Wow, look at that. Interesting soldering job. And all sorts of fun stuff going on in there. You can see that there's like insulating tape on there. Probably the same thing, basically just protection. So let's look at this board now that we've got that cover plate off. So, that's interesting, some little FETs that aren't installed very well. So these are actually the interesting kind of FETs where two of these pins are strapped together. I don't know if you can see that. Yeah, there you go. You see how they've kind of got this strapped together. So where are the ADCs? I wonder what these are. These are marked 699-3-R space 100K. I wonder if those are resistor arrays. Anyways, CD4066, LT1013, MC14053, MC34082, TLO32, 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 or LT1013, LT1013, TLO32, LT1013. Sounds like a pattern here. Hey, here's an LT1012. I don't see any ADCs. Could they be on the other side of the board? No. There's nothing down there. Are they doing like their own home roll dual slope on here or something, or what? MC14505, 74AC240, MC74HC393. I don't know. Weird. I don't know what the analog digital conversion is going on in here. Unless one of these chips is actually the ADC. But considering how many channels they have, it seems like there's not a lot of components on here. It's possible they're doing some sort of funky scanning with some of these FETs, because they've got, FETs here, FET here. There's a little tiny transformer. I don't know what they're doing with that. Lots of capacitors. Look at all the capacitors. Bunch of film caps. Interesting. Yeah, because there's nothing on the bottom side of the board. This is only a single... Oh, there's a bodge wire. And the only other thing I can think of is they're doing like FM modulation and then shoving it over the isolation barrier. That just seems weird to me. EKGs and stuff are... Well, they're not that hard to do. They're hard to do well, but that's true of just about anything that involves analog electronics. Let's see, I just unscrewed the wrong side. No, and then I broke it off. Or did I? Oh no, it's just cut off on the other side. That's wonderful. Let's see, I want to use my other screwdriver. So, yeah, so you can see down here we just have, oh, sorry, not on the camera. Just have, oh, cool. So here's the bottom side of the board. Oh, yeah, cable's caught. So there's a couple really interesting things down here, which is, the first thing, several bodge wires, and then the really interesting thing here is, look at this. Ground plane slices. Ground plane slice. So basically what's happening is, I would guess, is that this is the digital section. Yeah, so this section here this stuff here, not that. So right in this section here is the digital section. So this may involve, let's see if this works. It's rather bright, but where did I put my tweezers? So you can see we have a cut here, and then we have two, and these resistors are bridging the ground plane. There's a whole lot of shit going across the ground plane. I don't know, that's not the best layout. But this section here is the digital section. So what they're doing is they're containing all of the currents. So basically there's going to be circulating currents between these two devices here, and they're, by splitting that ground plane, they're preventing them from flowing out in here and interfering with some of the analog stuff going on over here. And then the other thing you see is that there's this gap here. So what that's to do is that's to basically, contain any circulating currents within the power supply, in this area. I'm actually not entirely certain why they even brought this plane under here unless it's for shielding purposes. Because again, this is all just running straight through this. None of these are connected to the plane. Oh wait, no, the central... Okay, yeah, the center tap of the transformer is connected there, so they did have to bring it out to there. It might also be for like AM, emission reduction or something along those lines. You can also see here's the isolation gap, bridged nicely by a sticker, which probably isn't a big deal, but whatever. Look at this little bodge wire. That's a cute little bodge wire. There's some cute little bodge wires up here. Yeah, I have no idea where the analog digital conversion is. These are interesting optos. They are CNW136, and they're one the other way. This is an MOC 8113. So, I could conceivably see one of these being analog feedback for the power supply, but I kind of strongly doubt it. Mostly because I would expect, it to be immediately proximate. That means they'd have to run the analog feedback path across all this digital crap, and then back across all the digital crap to the, the switch mode controller, which I'm fairly confident is that device there. So, some other interesting stuff, like look at this, you can see here, they've got some other ground cuts here, they've got ground cuts there as well. So they're, basically look at this, I bet, I bet this is like the ground, so they want to return these ground currents from the FETs, the pins of which are here and here. They want to return, so I bet what happens is, like with most of these, you tie the center tap high, and then you alternately pull the two ends of each of the windings low, and that's called a half-wave center tap, or I forget the terms, I'm so bad with words, or with nouns at least. And then, so what happens is they're returning the current here, and then actually if you look on the other side, you see that there's this big chunky tant right in the middle. So that basically they're going to be containing the switching currents for this power supply, basically the switcher. And then you can also see it looks like the other pin of the tant goes right back to the connector as well. And they may actually bring over multiple connections. I'm not too sure. Interesting. I wouldn't mind knowing what the power draw on this thing is, because they can't be getting more than, maybe 5 or 6 watts across with these little transformers. Even with, interesting stuff. Anyways, I'll put that aside for now. Oh, yeah. So, this should be fairly interesting, because this is going to be electromechanical. Also, it looks like I don't have to actually remove these screws entirely, I just have to loosen them. So here is our NIBP transducer. Oh wow, no wonder it was rattling. The pump is broken loose. Yeah. So there's the pump. And there's the screws that are supposed to retain the pump. And there's the pump not being retained by these two screws, which have vibrated loose from the look of it. Amused. There's some little solenoid valves. Oh no, wait, that's a pressure transducer, I think. That's the solenoid valve. So the way these work is it's these annoying little pop-it fixtures. So I should be able to just kind of shove my tweezer in there and kind of lift the center up. Wait. Something a little stronger. Or just break it. Well, that ain't going back together. Oops. So now this overall, the whole thing should kind of come out. I pull these out the right way. Oh fuck, they're latching, that's why. Assholes. Here the serviceability is 0. See, they're supposed to come out like that. So the way these work is you push them in, then you push this down and it spreads those pedals out and then they don't come out anymore. Oh, yeah. Huh. Hello, bod capacitor. I sure like these rubber feet on the back of stuff. And I got an email. That tube is not long enough, you people. Maybe it is, and it was just holding it left. So, we have our little power supply. Here's our pump. And here are the screws that are supposed to hold the pump in and are doing a piss poor job of it. That's interesting. Look at the vents. Anyways, so. Man, this thing is hilarious. So, man, look at this. So they've got these really ridiculous screws, you know, with like washers on them. Like these weird washers. You can see they've got these great big plastic flange washers on them. And then there's this, which is actually, believe it or not, industrial hook and loop fastened down. And then, of course, they don't put these screws on hard enough. At least sigh. Oh, yeah. This is a cool little pump. It's a dealer pump. They make all sorts of little specialty pumps. Oh yeah. So you see they've got these two screws which screw into the plastic and apparently have no thread lock or lock washers or anything on them because that would make too much sense. Bracket. So here's this adorable little pump. So there's going to be a little tiny piston in here. That's actually interesting. Let's take a look at that just because these amuse me. And I like pumps for some reason. Give you an idea of how warped of a child I was. I collected pumps at one point. I needed a life, I guess. So, we have here a little bronze bushing. And you can see here, this is not a piston pump, this is a diaphragm pump. So if you can see the little eccentric, that beige thing in the background moves up and down. So that actually just moves the diaphragm. And then this screw is actually a counterweight. And this is just the other end bearing. And this is actually, it's a spherical bearing with two flat sides and then a hole drilled through the center. And that allows angular adjustment. Basically this can kind of tilt around and then the bearing will self-center. Or will the angle will level. It's cool stuff. Let's actually see if I can't get into the top and take a look at the diaphragm. These things, the first thing that fails on these sort of things is the diaphragm wears out. I've had I have a bigger one that I used for like an airbrush, where the diaphragm ruptured and the whole pump basically went to hell. No longer worked. I was actually able to get it working again with some super glue. Didn't last that long, but you know, hey, didn't cost much either. Yeah, so there's the diaphragm. So you can see as this rotates, let's see. As it rotates, it comes up and then it goes down, and it comes up and then it goes down. So then in here, you're just going to have two. So actually, the way these work is, so that's just like a rubber sheet over a little hole, and when the pressure comes in, it flexes the rubber sheet up, and then when it goes the other way, it pushes it down. It looks just like a spring ring. So those are generally like fiber reinforced plastic or something. And then this outer ring just forms the seal. So if I pull this top off, it's pretty stuck on there. Basically, there we go. So you can see that here is just basically an exact replica of the other side. You know, just the opposite directionality, and then you can see that this is the seal. So this is basically just a single shot injection molded assembly. And then with some clever rubber gasket placement, it all seals up and then generates air pressure. Or vacuum. These are actually bidirectional. And then if you really want to abuse them, you can actually run fluid through these for a short period of time before they start to get all grumpy. So here's the pump running. You can't see it, but you can hear it. And it's definitely producing a fair amount of air. You can also see it's a hell of a lot quieter now that it's not like... Whoops. Shouldn't shut up. I mean, it's not like going... Not vibrating against everything. But it only draws... It's drawing 170 milliamps at 12 volts. So pretty low power. This little booty they have over the butt of the motor is really kind of amusing. Oh, I see why they've got it. It's because it's fucking spraying brush dust everywhere. I guess that must come with it. Anyways, I don't know why I'm putting this back together, but I am. Right. I'm sorry, that goes like that. Abusive slotted driver award goes to me, apparently. That's not a Phillips. So this just kind of sits in here, and I believe, oh fuck, which tube is it? So, and then it just kind of fastens down onto the hook and loop. So you can also see that they've got a, you know, so there's a little manifold down here. So all of these are connected together. So what these two tubes are, I bet, oh, I know what these are. So these are variable vent restrictions. So basically they need to be able to vent the pressure within the system at different rates. So I think these are small orifices. Small orifi. Small orifices, or something like that. You know, basically when they're letting the blood pressure down, you have to let the when they let the air pressure down, you let the air pressure down, you know, basically decay until you start to see the peaks of the waves, and then you let it decay until you start, you know, it stops seeing the bottom of the trough, I believe. I'm not completely certain I'm accurate on how you measure blood pressure. But, so basically they need to be able to bleed the pressure down at a controlled rate, and I'm pretty confident that that's what all those these funky fittings are for. You know, and then by having 3 of them, I think they can switch in different numbers depending on the volume of the blood pressure cuff. And they probably do some fancy pants runtime heuristics to determine, you know, to what extent they need to do that. You know, basically based on how many seconds it takes for the pressure to come up, they can determine the cuff volume. I don't know what all these little these came from. Probably not somewhere important. So here's the actual circuit board. And then you can see this is the actual pressure sensor. I'm not too sure what this is. This is probably like an overpressure switch. But you can see that this goes off to the actual blood pressure cuff, and then this, so that interface is there. Oh hey look, it's a ULN 2003, so that's going to be their switching element. So you can also see we got a really big cap here, which is kind of strange because I don't see, why would they put the capacitor there if there's no active switching elements here? Now basically they're going to have to be bypassing, there's a big inductor here. So the motor may go through a big inductor, through this big capacitor, through this common mode choke, and then to the power. That would be how I'd guess this thing's wired out. And I bet if you look over here, there's this chunky FET, and I bet that switches the motor. Because these are probably not going to take very much current to switch. Also, these are loose too. Oh, they're fucking held on by plastic snaps. What the fuck, man? Oh no, they're held on by the fact that they're goddamn soldered down. That's high quality. So we can see here we have a Dallas DS1244 battery-backed SRAM is what I think that is. Got an EEPROM. And then we have N80C196 from Intel. So I think this may have been, they may have farmed this part out, I'm not entirely certain. But you can see that, you know, here's the pressure sensor. This is a 4-layer board, incidentally. You can tell from the fact that there's an internal plane. I don't know where the pressure sensor is connected. It might have like an internal F to V. Though I kind of doubt it because there's analog stuff over here. So here we have an OP400. Here's another one of these BI parts, 699-3-R space 10K. This could be another resistor element. DG201 ACJ. Here's another OP400. LM324. Here's another one of those BI 699-3-R space 10K. That makes me really think those are resistor arrays. Actually, let's see. Yeah, 10K. So I think I'm seeing unused resistors in here. 10K basically. Yeah, so it looks like this is a whole bunch of resistors in a box. I don't know what the tolerances are. Yep, 9K, 9K, 9.22, 9.22. Yeah, it looks like these are those floating. Oh, I'm not too sure how this stuff is all wired up, but yeah. So I don't know where they're doing the ADCs. Well, this is interesting. That's Altera branded, I bet. I see that A. It looks like the Altera A. This is probably another PAL, but it's a SRDIP. Yep. EP320 IDC. Wow, that's an UV PROM PAL. Got a little window on it. That's amazing. PAL or a CPLD possibly, though I kind of doubt it. Here's an AD7226 KN. That looks, that wouldn't surprise me if that's like an analog digital converter. 74HCT573, Max 232, another 232. Look at this giant ass connector here that wasn't connected before. I wonder what that's for. Maybe debugging. This is Rev AB. Is that Rev A or Rev B? Yeah. So, and then you've got some, you know, some epoxy blob tants. And then this is the ULN 2003, and then there's a Q1 here. So I bet this and this comprise the power drivers. Yeah. And then you've got this PT2, which was connected here. So there's that's how I guess the blood pressure monitor is made. It's old school, but functional, I would bet, if I had all the stuff I need to actually hook it up. Oh, I know where those plastic washers came from. They came from between the board and this. Alright, well that's about it. Well, let's take a look at the printer. What holds you in? Just 2 screws, I think. This is probably going to be kind of unexciting. Thermal printers is thermal printers. This thing sure has a really dense connector. Thing seems to be held in by 2 screws. Yep. 2 screws in the frickin' back plate. Is that how this comes apart? Really? Yep. Where is my long Phillips driver? Fall on the floor. The fuck? I'm just so lame. There it is. It's caught under the circuit board. So, there are 2 screws way the fuck down in here. There's one. And there's the other. Yep. So, that is what held this bracketry on. And it just comes right out. And then the screws make a mess of themselves. Are they captive? Yeah, they're captive. That's brilliant. Yeah, so I think that's about it, actually. So literally, there's general scanning incorporator, recorder product division. So we have one great big company branded ASIC, some line drivers, a crystal, the bus interface, and a motor. That's it. So that's just going to be the feed roller. And then the thermal print head is somewhere. Yeah, so the thermal print head's just right there. That's the print head. Not much to it, is it? Paper just comes right out. Just kind of roll it back up. I wonder if there's a particular way it's supposed to go on. Oh yeah. I'm installing the paper wrong. You're doing it wrong. Level printer. I wonder if I can power this up on the desk. Just completely taken apart. Let's see if I can. For science. So, I think I'll actually screw this board on at least. Yep. Of course, putting it on the right way around might help. Oh yeah. So you plug in there. printer. I think I flipped the ends around, but whatever. Plugs in there. But get some of this wire and these screws out of the way. So the screen plugs in here. That's an empty packet of. I can just kind of go like that. Where are you touching? What is it actually resting on? Boards. Right. Grounding? We don't need no stinking grounding. Yeah, the noise is in the display. But hey, it seems to be powered. It's alive! Apparently whatever all this stuff is on this little interface board is apparently not needed. Oh, apparently it is. Never mind. I made it sick again. Seems like I can't fake it into thinking there's an actual blood pressure cuff on there by sticking my thumb over the tube. Deflate, unable to measure. So actually, I wonder if all it needs is this board to make it think that it can perform an acquisition. Now it's plugged in. So it's interesting that it can fail on acquisition and yet pass the self-test. I guess the self-test isn't very thorough. Oh, you know what? I also realized I never plugged in the SPO2. Or did I not disconnect it? It is still connected. Oh. No wonder the acquisition's failing. So apparently, acquisition, quote-unquote, doesn't involve any of this stuff. I'm kind of tempted to scope those signals and see what they look like. Didn't I? That's interesting. So now it seems to be working again. Still makes a ghastly noise. Is it gonna stop? I guess it's bored. Oh, oh wait, it's gonna do it again. Maybe that shouldn't amuse me so much. Power draw goes up a hell of a lot. It's drawing an amp and a half. Oh, it got angry. It doesn't know what's going on. I should try and track down a blood pressure cuff before I totally destroy this thing. Oh, anyways, so there you go. There's the internals of a rather interesting little setup. I may do a second video on looking at some of the analog signals. We'll have to see what I feel like this weekend.